Hello everyone, my name is Gürkan Solmaz from NEC Laboratories Europe in Germany. Today I will present the paper CountMeIn Adaptive Crowd Estimation with Wi-Fi in Smart Cities. This paper will be presented in IEEE PerCom 2022 conference, and it is co-authored by Pankaj Baranwal and Flavio Cirillo. CountMeIn is a crowd estimation system with Wi-Fi in smart cities. The main motivation of the CountMeIn comes from the wide use of pervasive sensing in smart cities, and there exist systems including wireless sensors and other sensors such as street cameras. Crowd estimation is particularly interesting problem because of its possible applications to smart cities, such as crowd management, tourism retail service, evacuation modeling, and epidemics monitoring. There exist currently Wi-Fi-based systems, which are alternatives to the computer vision, purely computer vision-based systems that mainly use cameras for counting people in a given environment. And these Wi-Fi-based systems are mainly privacy and energy preserving alternatives to the computer vision-based applications. At the same time, there's a drawback for most of the existing systems because they lack accuracy in terms of crowd estimation and also adaptation to the dynamic changes in given environment. And dynamic changes can be different mobile devices, vehicles, or it could be also crowdedness levels in a given environment. Therefore, we consider CountMeIn as an adaptive system, which is based on machine learning for accurate crowd estimation. Here, we would like to give a background on the crowd estimation problem using Wi-Fi. On the left side, you see a raw Wi-Fi prop packets count graph for a given week, where the y-axis means the people count coming from the raw Wi-Fi prop packets only. And on the middle, you see RSSI-based filtering, receive signal strength indication-based filtering, applied to the same prop package count. And on the right side, you see a people counting camera input, advanced people counting camera input for the same environment. We see a huge discrepancy between the outputs coming from the Wi-Fi prop packets from the wireless scanner, Wi-Fi scanner, and the people counting camera, which is more reliable because it is also configured for the given environment. So the main problem here is the Wi-Fi prop packets counts do not match the camera counts. And only RSSI filtering or simple heuristic approaches, they don't seem to solve this problem. On the other hand, we observe certain patterns in both of these, in all of these three graphs. In terms of Wi-Fi prop packet count data and the camera, there exists certain patterns that we observe initially. And our question was then, could we calibrate the Wi-Fi measurements with a machine learning using a certain ground truth data for a short time period? Here is a deeper look onto the patterns that I mentioned. Here you see a 2-week time period given the day index from 1 to 14. And on the y-axis, you see the Wi-Fi prop count, Wi-Fi prop packet count. And we observe in this type of graphs, mainly there exist certain patterns, hourly pattern. It could be an hourly pattern during the day. It could be a daily pattern, or it could be even a weekly pattern. Then our consideration was we could use these temporal features in the temporal domain also as inputs to the machine learning, along with the Wi-Fi inputs. But there exists a caveat when using machine learning that we need to know which granularity should be the best for providing to the machine learning the temporal features. whereas, for instance, higher granularity may cause overfitting into the model. So in our observations and also in the paper analysis, we mainly consider using the hourly and daily day and hour information as the temporal information. And here is the optimization problem for the given total number of hours for a longer time period. CountMeIn approach mainly combines the raw Wi-Fi and camera measurements for the short-term training period for a machine learning model. Here on the left side, you see a training period. So during the training period, we consider a people counting camera, which is accurately counting people in the given environment, and a Wi-Fi scanner in the same environment. And here you see people having mobile devices. Some people may not having mobile device or not activated wireless functionality. And for those type of reasons, Wi-Fi scanner has a different count than the people counting camera count. As here we show the similar graph, this time all together with the Wi-Fi counts and the camera counts for the people counting in the same 1 week time period. And the general idea is to do this training period as short as possible, and then apply this training based on the learning these patterns between the Wi-Fi counts and the camera counts, and apply this training to a longer crowd estimation period. So here, CountMeIn analytics basically replaces the machine learning, replaces the camera using machine learning. And the question is, could we only rely on the Wi-Fi scanner or Wi-Fi counts? And using the analytics, could we estimate correctly the crowd estimations? This approach also enables long-term estimation because it is learns different dynamics on the environment in the smart city, so it could be applied in a longer term also. And another idea is to replace the camera, meaning we may not need a camera for a longer period of time, other than a short training time period. We may replace it with a machine learning approach. And the same camera could be used on other places as well. This would also save from the cost of deployment for advanced cameras, especially. Here is the CountMeIn system architecture in more detail. We have a set of steps here from top to bottom. You can see here we describe simply describe what is the main items. On the left side, you see the Wi-Fi information. On the right side, you see the people count information from camera. And in our architecture, we have a certain data pre-processing steps until the end of the feature selection. We call it the data pre-processing steps. And then we have also the people counting camera inputs coming to the training. And here we have transformation from a raw sensor data into a more consumable database structure, and then aggregation for a given time slices, time windows. And then we have different filtering approach for RSSI filtering and also to remove static devices. And then per packet counts after the filtering is applied to the training. For the training, we consider different machine learning models, which have two different types. The first type is the polynomial regression models. The second is neural network models. And after the calibration, the idea is to provide the crowd estimation through the machine learning model and visualize in a dashboard. We tested different machine learning models, as I mentioned. The first type is different polynomial regression models. For the polynomial regression, we tested with ranges vary from 3 to 12. And we noticed And certain regression models have problems such as overfitting and multicollinearity problems. At the same time, to address this problem, we use the regularizers such as lasso regularizer and the ridge regularizer. In the second set of machine learning models, we consider the neural networks. Neural networks are known to successfully represent nonlinear relationships in the data. And at the same time, we know that they are also prone to overfitting. For this reason, in our neural network model, we began with a relatively small, very small architecture, neural network architecture, then gradually make it a larger model. And from the test, our best neural network architecture had the total number of more than 3,000 parameters, and consists of 6 dense layers, as mentioned in this table. To test the data, to test the machine learning, different machine learning models, we consider testing data from our previous pilot study in Gold Coast, Australia. This was a pilot study that is conducted in collaboration with the NEC Australia. And from this pilot study, we considered a data set of 5 consecutive months where we had the most availability for the wireless scanners as well as people counting information from cameras. And the testing data includes data from pedestrian shopping street in Gold Coast as well as the near beach area. And as mentioned, this data set includes mainly Wi-Fi scanner counts and people counting camera counts. For the evaluation, we try to avoid the possible bias that could arise by using only a single statistical metric. As every statistical metric has a certain bias, we considered, based on these biases, we selected 4 different statistical metrics that are listed here. And we tested with all these metrics for the experiment. Other than that, we implemented a state-of-the-art model that we found in the literature called Pedestrian Flow Analyzer, as well as a crowd estimator model, which is another state-of-the-art model that is previously studied by us. But this model didn't consider the replacement of a camera, but it was assuming the camera is available and considering the camera correlates adaptively correlates the Wi-Fi, calibrates the Wi-Fi. Whereas in this new model, we don't even consider the usage of camera in the crowd estimation period. And the pedestrian flow analyzer is using various techniques, such as different filtering techniques, to understand the crowdedness in a given environment. We tested our approach using RSSI filtering, as well as also not using RSSI filtering, and different machine learning model choices. Lastly, we also tested the scalability, considering an edge device that we created in the lab environment to see if this model, including the pipeline, including camera wireless part, as well as the machine learning, could we run it on a simple edge device in the lab environment. Let me now have a look at some of the results from the paper. First graph shows the math error for the lasso and ridge regression regularizers. And we have seen in our test, we observed the lasso regression mainly provides a more stable performance even for a dynamic change when dynamic changes happen in the data. On the right side, we tested which would be the best training duration for the training period. We tested the different weeks, such as 1 week, 2 weeks, 3 weeks, and 4 weeks time period for different months. These 5 consecutive during these months that we had the data set, and here we observed the best performance comes from 2, 3, and 4 weeks. And considering shorter time period that has advantages of the shorter time period, we considered 2 weeks as the best possible training duration for this application. We also compared different neural network models, and the details of these different models are included in the paper, each of these models. And here we see the Adam optimizer with the root mean square error-based loss function had the best performance for all of these 4 metrics. Other than that, as mentioned, we also tested the pedestrian flow analyzer in the same data set. And we considered here we consider minute level based performance as well as hourly performance. And we observed that in general, CountMeIn achieves crowd estimation error reduction substantially. For minute level, it achieves 44% in the root mean square error. And for the hourly level, it achieves 72% error reduction based on the root mean square error. Here, we also include the error from the raw Wi-Fi pro package counts. As you see, the errors substantially decrease from, for instance, for the RMSE, they decrease from 19 to 3.72 for the minute, and hourly it reduces to 0.91. And interestingly, we noticed, considering all these models, raw Wi-Fi pro package count, pedestrian flow analyzer, and the 3 different CountMeIn models using RSSI filtering and not using RSSI filtering, as well as using polynomial regression or neural network model. In all these 4 metrics, CountMeIn with a neural network provided the best performance. That shows a clear winner for these approaches. At the same time, polynomial regression also provided a substantially better performance than raw Wi-Fi, as well as the pedestrian flow analyzer method. And the trade-off could be from the polynomial regression and neural networks can be the training computation. In this result, we have the raw Wi-Fi pro package count-based errors given these 2 metrics, the statistical metrics, MET and RMSE. We see the raw Wi-Fi errors here from 0 to 50, whereas we see our model here, CountMeIn, on the top, on the bottom left part of the slide. As you see, there is a substantial, not only substantial decrease in the errors, but also there is certain stability. There is not much fluctuation in the errors given different, considering different weeks for these calculations. On the right side, you see the state-of-the-art models, crowd estimator and pedestrian flow analyzer. And we see crowd estimator is not able to adapt to the changes after the camera, after the people count information is not available. As mentioned, we also applied this approach into the edge devices. Here, our goal was not to test the crowd estimation in a lab setup, because this application is mainly considered for a larger scale, such as a city square or some urban environments. But here our goal was to test if we could apply the same model on a small device such as a Raspberry Pi 4. If this is the case, then that means we could also do in a larger scale. We could have edge devices that do this computation without sending maybe any data to the cloud, doing all the computation on the edge device. It would, of course, save from certain bandwidth cost, as well as other considerations. Here you see we integrated the fisheye cameras, 4 fisheye cameras, considering a larger angle, and we used the Raspberry Pi 4 device as well as a Wi-Fi adapter in this lab device. And we considered the scalability in terms of 2 weeks training data. The question is how much time it would take in an edge device to train, given a 2 weeks training data for Wi-Fi and people counts. On the right side, you see the table for different polynomial regression degrees from 3 to 8, training time on the PC, normal personal computer, and the Raspberry Pi device. And as you see, this time for training is almost negligible, considering a 2 weeks training data. And in the worst case for degree 8 for polynomial regression, it cost less than 10 seconds for both PC and the Raspberry Pi. Other than that, we also observed the maximum for polynomial regression models among the ones we tested with degree 12 was around 37 seconds. And lastly, neural networks. Applying neural networks onto the same training data would cost 27 minutes, which is 43 times more than the polynomial regression model to complete 150 epochs. So here there is a certain trade-off between the training time of a polynomial regression and a neural network model, where polynomial regression has a shorter training time. At the same time, neural networks provided better accuracy for the crowd estimation. As a conclusion, in this paper, we propose CountMeIn as a novel adaptive machine learning-based system for crowd estimation using Wi-Fi. CountMeIn provides accurate and long-term crowd estimation for smart cities. In the paper, we showed that CountMeIn provides state-of-the-art results, considering minutely and hourly crowd estimation, as well as the model is also convenient for on-device edge processing. The main benefits that we consider for CountMeIn is to minimize privacy invasion by reducing the time of usage for cameras, and minimize the deployment cost, considering a possibility for reusing camera in different environments instead of deploying many cameras, especially for advanced people counting cameras, as well as long-term energy consumption due to in the long term relying only on the wireless information, which is substantially smaller than the information that would come normally from video to the cloud. We consider a pervasive sensing application to smart cities for crowd estimation would be possible in models such as CountMeIn, as well as the future models. Thank you very much for the listening our presentation, and for any questions, please feel free to reach me out by my email address. Thank you.